Hey, what's up? Let's do some physics. Watch this. Oh, I got super tiny. Now I'm over here on the side. Um, we need to first finish what we were talking about yesterday, which was we were looking at a parallel circuit where two resistors were in parallel. So we had this circuit with a 10-volt battery, and there's two resistors down below the battery. So if we want to investigate how those resistors combine, like we saw on the other page that when you have two resistors in series, you can combine them just by adding them together, and practically you could just replace those two resistors with that one resistor and the circuit is the same. So I want to do the same thing and figure out how you can combine resistors in parallel and get the same total current basically in this circuit. So we know the total current is 0.2 amps. So what one resistor could I replace these two resistors with and get 0.2 amps? Well, if you think about that, that circuit would look like this. Just one resistor. This is 10 volts. We want to know what that resistance is. If we take Ohm's law and use it on this resistor, that's V equals IR. The resistor sees both ends of the battery, so we know the voltage difference across this resistor is 10 volts. So 10 equals, I know that I want the current to be 0.2 amps times R. R turns out to be 50 ohms if you do that division, 10 divided by 0.2. And that's half of either of those resistors. So it wouldn't be quite as easy if they weren't exactly the same resistance, though. So let's see if we can develop a formula just in general that will let us figure out what resistance we can replace resistors in parallel with and have the same circuit. So if you look back up there, the total current is I1 plus I2. And I1, we calculated, there's an equation right here we got. It's the voltage across that resistor divided by R1. So I2 is also the voltage across R2, which is the same. Things in parallel, resistors in parallel have the same voltage difference by definition. Like if they're not, if you think some resistors are in parallel and they don't have the same voltage difference across them, then they're not actually in parallel. Okay, so that's V over R2. Remember, we're just writing down that the total current, 0.2 amps, is each current added together. 0.1, that was 0.1, that's 0.1. But we're doing it with symbols down here. This circuit that I drew, that I replaced my original circuit with, this is really, if I look at this circuit and I say V for this resistor, let me call this resistor R total now. The voltage difference across this resistor is this. The total current is this I, and if I label that RT, I can plug that in. I can replace I using this equation. So I would get voltage over RT equals V over R1 plus V over R2. And then look, there's a V in each term. So if I divide both sides of this equation by V, I'm just left with 1 over RT equals 1 over R1 plus 1 over R2. That is the relationship for resistors in parallel. It's not as simple as the series one, and if there were more resistors, you would just keep adding. If there's 3 resistors in parallel, you just keep adding. If there's 4, you just keep adding like this. 1 over R5, dot, dot, dot. And the trick, if you use this to figure out a total resistance, make sure you divide and then you add, and then you divide, and then people will stop at that point, but you don't know the resistance, then you know 1 over the resistance. So the last step is that you have to take the reciprocal to get the actual total resistance. So if we try this with our numbers to verify if it works, 1 over RT equals 1 over 100 plus 1 over 100. I know that I should get 50 ohms from a while ago. So that equals 2 over 100, which is 1 over 50. So 1 over the total resistance equals 1 over 50. If I just take the reciprocal of both sides, then I get R total equals 50 ohms. And it works. Okay. Next thing we got to talk about is power. In electrical circuits, this is a pretty fast one. Power in an electrical device can be calculated as P equals the current going through that device times the voltage difference across that device. Current through, voltage difference across. So I keep saying this, voltage difference across device. That's the vocabulary that physicists and electricians use to talk about if you measure the voltage at one end and you measure the voltage at the opposite end of some electrical device and you subtract them. Current typically goes through things, so we say current through a device. Many of the times that you calculate power in a circuits problem, you'll be talking about the power through a resistor. So power dissipated by a resistor. So resistors don't actually do anything. They're not taking energy and doing useful work. All they do is heat up. So really, when electricity goes through a resistor, it just wastes energy by warming up. And the language that you'll often see is that power is dissipated, or it's it doesn't disappear, it turns into thermal energy. But that thermal energy is usually not able to be captured and can't do anything useful with it after that. So we say dissipated by a resistor. So on the last page, that resistor in the total circuit, it was 50 ohms, and a current of 2 amperes went through it, and there was a voltage difference of 10 volts across it. So if you wanted to calculate the power through that resistor on the last page, you would do I times V, and you would get 2 amps times 10 volts, and that would give you 20 watts. There's the bell. I will let you verify that an ampere times a volt is a watt. I promise it is. Maybe that'll be a homework problem or show up on a test or something. There's 2 very common shortcuts you can use to calculate power in a resistor, and really they just come from combining the power equation for an electrical device and Ohm's law. If you do that, you can eliminate either current or voltage. So if you eliminate current, then you can solve this for current and plug that in over there, and you get V, then there's another V, so V squared over R. This is not centripetal acceleration, even though it looks like it. This is voltage difference across a resistor, squared, divided by that resistor, gives you power. It comes from the IV equation, so it's not different. You just use it with Ohm's law. Or if you want to eliminate the voltage and be left with current, you could just plug in V equals IR, and you would get I times IR, or what it's usually written as is I squared times R. These 2 equations give you the same value for power if you use them on the same resistor in a circuit. It's just that sometimes one of them is more convenient to use than the other one because you might not know the current through a resistor yet, but you might know the voltage. Or you might not know the voltage across the resistor, but you might know the current. So these two equations in boxes are probably what you use most when you calculate power through a resistor, rather than going and finding current and voltage, because it's usually more work to find current and voltage if all you're after is the power value. All right, next thing I need to talk about is EMF, electromotive force. EMF is a really unfortunate term that sticks around. It is a holdover from really early days of electricity where they thought that it was easier to describe things in terms of force. It's basically just the voltage of a battery. And there's no difference between EMF and voltage. We will learn in the next section of topic 5 that EMF is technically the voltage between the terminals, voltage difference, I should say, between the terminals of a battery with no internal resistance. So this is like we call that an ideal battery, because real batteries are made of conductors that do have some resistance. We're not talking about real batteries until the next section, though. That's the best definition for EMF. And the symbol for EMF is lowercase Greek epsilon. It looks like a backwards 3, kind of. So when you see this symbol in a circuits problem, it just means the voltage of the battery. The voltage of the battery. And there's really I wish we would stop using the term altogether, because there's no point. We already have the idea of potential difference and voltage. We could just say the voltage of the battery. And in fact, I will say that a lot. But if you see EMF, you should know that that's what it is. Right. Last thing I need to talk about is the resistance formula for a real conductor. And my app just crashed. Okay, it's back. Cool. So, resistance of a wire. Real wires have more resistance if they are longer. They have less resistance if their cross-sectional area is larger, and they have more resistance if a quantity called resistivity is larger. That symbol looks like this. It is Greek rho, lowercase. I think we used it for density one time before. So the real resistance of a wire can be calculated like this. And rho is called resistivity, and it's a characteristic of the material. Used to make the wire. So you can look up resistivity values, just like you can look up coefficients of friction for different materials. You can look up resistivity for different metals and different materials. And you'll find that conductors have really low resistivities and insulators have really large resistivities, because if this rho is small, then R will be small. If this rho is large, then R will be large. If L is large, R will be larger, and if the cross-sectional area of the wire is large, R will be smaller. You should think about the number of collisions that electrons make with atoms as they think about collisions of electrons with atoms. So if you're thinking about how likely it is that an electron will collide with an atom in a wire, the longer the wire, the more time it has to collide with an atom, and the more atoms it passes. So there's a higher chance that it will collide with an atom and it be slowed down, and the current will have more resistance. So longer wires have more resistance because the electrons have more chances to collide with atoms. But if you have a tiny wire versus a large wire, so this is the cross-sectional area. If you look at the end of the wire and we cut the wire and you look at the shape, that's cross-section. Cross-section, big A, little a. If you're an electron trying to go through this small wire, you have less available paths to travel through. If you're an electron trying to travel through this giant cross-section, you have more available paths that you could take and avoid atoms. So a thicker wire actually has less resistance. Often thicker wires are used when you need lots of current, because if you didn't use the big wire like this, the resistance of the small wire would be too large and it would get too hot. The units of resistivity, if we just look at the equation, we know that it needs to end up in ohms because resistance has ohms. So resistivity units are ohms times meters squared, because it needs to cancel out the meters squared on the bottom, divided by meters because it needs to cancel out the meters of the length. So these cancel to give you just ohms times meters. The units of resistivity are ohms times meters. And I think I hit all the different topics I was going to talk about. Let me see. Things to cover. We did that. We did that. All right. Yep. We'll work some example problems on Tuesday using some of this new stuff that we just saw. Have a good weekend.